Hello everybody and welcome back. So this video we're going to look at how do I calculate what the voltage drops are actually going to be across each of my loads and across each point of my circuit. So we have to make sure that we're able to understand, we have to be able to understand Kirchhoff's voltage law. And he said that the algebraic sum of the voltages in a closed loop has to equal 0. Another way of saying it is that the voltage rise of my circuit, or my source voltage, has to equal all of the voltage drops within my circuit. And that's kind of the law of conservation of charge when we used Kirchhoff's current law as well, that all of the energy has to exist within the circuit. It can't just disappear. It has to exist in some form within that circuit. So when we're going through and analyzing Kirchhoff's voltage law, we have to be able to understand what his law was stating. We also have to make sure that we have all of our polarity placed and all of our polarity placed correctly. I believe in the last video I forgot to mark the polarity of these two loads. So if that's on your piece of paper, if you're going through this, this should be a negative, this should be a positive here, and a negative and a positive on that load. I believe I forgot to do that in the last one. We need to be able to understand that polarity, and we have to have that polarity plotted correctly, and we use it with the direction that current is actually flowing through the circuit, from negative to positive. You can use conventional flow with positive to negative, you just need to do that through the entire circuit. Both are just as accurate. So if I'm going to solve and calculate what some of these voltage drops are going to be, I'm going to need to transpose Ohm's law formula to figure out what voltage is. And at each individual point, when I have an amperage and an ohmic value, I can calculate what that voltage drop is. The voltage drop is going to equal the current times the opposition to current flow. That's what's going to give me my volt drop. So if I look at this, the voltage across this component, the volt drop across that conductor would be 22 amps times 0.1. So if I were to measure, I would have 2.2 volts across that component. So, and I'll just work my way down. If I have 5 amps and 0.1, still utilizing this formula, V equals I times R, I will have half a volt, 0.5 volts across this component. Okay, that's what is across the volt, that's the volt drop across my neutral conductor. If I look down here, I would have 1.7 volts across this conductor here. The volt drop here would be 0.7 volts. And the volt drop across this conductor here would be 0.7 volts. So now that we have these values, just by using V equals I times R, we can analyze. We can use Kirchhoff's voltage law and look at these closed loops. I have many closed loops within this circuit. There's lots of ways to analyze this circuit. And at the end of the day, they all have to work. If you close the loop, if you start here and go all the way through this, it should equal 0. If you plug this into your calculator when we're all done, every loop that you create, if you do all of the voltages, including the source, you should have 0 show up on your calculator. Okay? If I just look at the voltage drops, if I add the voltage drops together, they should equal what my source voltage is. Okay? So if I look at Kirchhoff's voltage law, okay, and it's how we start within our circuit. How do we actually want to transpose Kirchhoff's voltage law to figure out what the voltage across load 1 is actually going to be? And it's the algebraic sum. So we're adding these values together and paying attention to those negatives. All right? So I like to kind of start at a point and then work my way entirely through that circuit. So from here, we can start right at this plus sign. So the very first thing that we are going to do is add. So if I want to calculate, we're looking at the voltage across load 1. Okay? So I am going to say positive 120. And remember, we are adding these together. Okay? If you need to put these in brackets to remember that that's individual values, that's fine. We are adding this together and paying very close attention to polarity. So I'm at a positive. I go to my next load. The very first polarity that I hit at my next load, that's what I will add. So I'm actually adding a negative 2.2 volts. And I agree with you, that's the exact same thing as subtracting, but I like to keep it consistent. I like to remember that I'm adding these voltages together and paying attention to polarity. So I'm adding a negative 2.2 volts. Okay, I'm unsure what this is. This is what we're calculating. So then I'm adding another negative 0.5 volts. Okay, and this is what I am going to use, and this is how I'm going to solve for what that voltage actually is. So what I do, 120 plus a negative 2.2 plus a negative 0.5, I should come up with 118.3 volts. So this is what I can encourage you to do. Does Kirchhoff's voltage law, is it in this circuit and in any circuit? Okay. Is it accurate? Close the loop. Start at the beginning and do every value. Will it equal 0? Will positive 120 plus a negative 2.2 plus a negative 118.3 plus a negative 0.5 equals 0? If it does, you've done this correctly. If I continue, and let's go for load 2. So the voltage across load 2. We can do that exact same principle. Pay attention to polarity, because the polarity, depending on the direction you go, the polarity that we're actually going to utilize here now is going to change slightly. So I'm going to start at this positive symbol, okay? So positive 120 plus, now it's a positive 0.5. We are unsure of this. This is what we're solving for. So we're plus a negative 1.7. When I calculate this, 120 volts plus a positive 0.5 plus a negative 1.7, I'm going to end up with 117.8 volts is the voltage across this load. 117.8 volts is what I would measure across that load. Now the last thing I have to do is the voltage of load 3. And I have a couple of different ways that I can do this, because I have many closed loops now. I can start from the source and do the entire perimeter, or I can just utilize from this load. What's important to remember now, it's no longer 120. We do not have 120 volts across my loads. I have 117.8. So if I'm going to analyze this circuit, I have to make sure that I am using those values across each of my loads. So for me, I like to start from the source and I like to do the entire perimeter. So I will have a positive 120 plus a positive 120 plus a negative 2.2 plus, and I'm going to continue on this loop, a negative 0.7 we're unsure of this value here, that's what we're trying to solve for. So I'm plus a negative 0.7 plus a negative, sorry, put that in the wrong spot. Quickly get rid of this. Of course it has to smudge on me. There we go. So we're going to add a negative 1.7. And then I'm back at my original starting point, so I have closed the loop. So when I add all of these values together, I will come up with 234.7 volts. That's what I would measure across this load. So what we can look at now is, does this make any sense? What type of load would I connect here? Well, I would want to connect a load that was rated for 120 volts. And do I have close to 120 volts? I do. So therefore, I would get close to rated output. And if a lot of our equipment will have a voltage rating of something, so this could be, say it was a light bulb. A lot of our equipment would have a voltage rating on it that would say 115/230. Okay? That's what would be on the box. That's what it would say right on the light bulb. Sometimes it says 110/220 as well. So why do they give this voltage rating to a piece of equipment that theoretically we would apply 120 volts to? What they're doing is after my line loss, after my volt drop that exists across the conductors, I would still have slightly over in this case, but that's not a dangerous situation. Okay, that's just fine. I will have essentially rated voltage across my load, therefore I will get rated output. So I used in this case, 115 volt load, and I have relatively 115 volts, 118.3, I'll have rated output. This load back here, I connected it to my line 1 and line 2, or my negative, my positive terminal. It would have a rating of likely 230, close to 240 volts, probably 230 again. Do I have close to rated voltage? Absolutely. 4.7 volts excess is nothing we have to worry about when we're talking about ratings. So I hope this has helped. We can continue to do these. What I encourage you to do is go through many of the loops. If I continue to close the loop, does it equal 0 each and every time? I hope this has helped. We'll see you in the next one.